Hello and welcome to this webinar from Tucson Photonics, Imaging Science as it Moves. So today we're going to be examining how we can capture moving samples and moving imaging subjects with our scientific cameras. Just to briefly introduce myself, I'm Dr. Keal. I'm a scientific and applications consultant with Guido Scientific. And for the last 3 years or so, I've been doing work with Tucson Photonics. My background is in physics, but for the last 8 years or so, I've been in the scientific camera industry. So just to briefly introduce Tucson Photonics a bit more thoroughly. So this is a large camera company based out of China and Singapore and have quite a global presence with all sorts of teams performing all sorts of functions all over the world, including an office in the UK, in Birmingham. And they're a large company that have, just to give an example, 6 engineering teams, meaning that they can run 6 projects simultaneously. And alongside the over 200 staff that work for Tucson, they're a very impressive force in the scientific camera market. The markets that Tucson mostly serve include bioinstrumentation, so that's including cameras within instruments that might be sitting on your lab bench right now. We have advanced inspection applications such as semiconductor inspection, where the needs for scientific cameras are very much present, even though it's a more industrial application, more of the cutting edge of what's needed for these industrial applications. And then finally, of course, we have academic research, fluorescence microscopy, biophysics, have soft X-ray and extended UV cameras as well, alongside cameras for astronomy. So, on to thinking about our subject for today. We're just going to briefly introduce a quick overview of some of the example applications where you might come across trying to image something either that has movement inherent to what you're trying to image, or the technique that we're using involves movement. One quick example might be trying to image an animal brain, where here the movement is more likely to be from trying to scan and tile and stitch our way across a very large sample. We also might have single molecule tracking techniques and other applications where we've got a fairly weak fluorescence signal that is moving, and we're trying to capture some of the dynamics of that movement and understand what's happening. We've also got, once again, advanced inspection applications, like in the case of PCBs, where these might be moving at high speed along a production line, and we're trying to capture them as we go for quality inspection. We've got the very broad area of cell biology, all sorts of techniques that can be found here, many of which involve either capturing movement within cells and dynamics of these systems, or again, the technique can involve motion as we tile and stitch our way across a large sample to get good population and statistics. We've also got web inspection, other advanced inspection applications where we again have very high speed movement that we're trying to capture. And finally, we can have imaging things within flow cells, whether this is microfluidics or, for example, flow cytometry, very, very common application for trying to image things that are in motion relative to our camera. Broadly speaking, we can split many of these applications, or rather I should say many of the techniques within these applications, into a number of separate jobs within moving imaging subjects. And the first one that we can think about is we're trying to capture some form of motion relative to a stationary camera. And the key thing with this is that the motion might not be predictable. It might be, in various directions with various velocities. We might be trying to capture that motion and characterize that motion, but in general, we can't really predict what's happening with the motion, and we're just trying to capture it as it occurs. The next 3 jobs are somewhat different. We have, on the one hand, ongoing live analysis, where we might have a flow cytometer again, where we've got cells flowing past a stationary camera, and we're maybe trying to extract some data about those cells, and the image of the cell is not necessarily the primary output. It's something that has come out the other end of analysis pipeline that's our primary output. But here, usually, the motion is somewhat inherent to the technique of imaging that we're using. Similarly, if we're trying to do tile and stitch, again here, motion is inherent to the technique. So in this case, of course, the yellow box shows the field of view of a single camera frame, and we're moving our stage or a gantry if it's larger scale objects that we're trying to image. We're moving our stage from place to place and stitching together a larger scale image. And finally, we might have some uniform motion, again, such as a microfluidic cell or web inspection or whatever it might be. And we're trying to capture a movie or capture single frames or whatever it might be of something moving with relatively constant, relatively uniform motion past a stationary camera. And this has to be treated slightly differently from this first job, and there's some other interesting opportunities with this type of job, which we'll come to later. So, what kind of problems do we encounter? Obviously, motion blur is a very significant part of this, and this is true no matter what form of photography you're doing, as in the case here. When we're doing consumer photography, the classic example is sports photography. Things that move during the exposure of your camera will spread out the light that they send to the camera across multiple pixels, resulting in a blur. If you're trying to counter motion blur by using a short exposure time, as we'll explore in greater detail later on, you can come across problems with having low signal due to that low exposure time. And finally, we can have these rolling shutter artifacts. If you're not already familiar with rolling shutter artifacts, trust me, this plane propeller should not look like this. And how exactly this forms, we'll explain shortly as we explore how a very common form of camera, the rolling shutter camera, how that actually works. Also, though, to quickly note that in many of these applications and techniques, speed and data throughput limitations can also be a really significant problem. And I just wanted to note, although we're not going to really talk about camera speed and high data throughput in terms of pixels per second today, high speed and high data throughput cameras is a particular specialty of Tucson Photonics. So if this is an area that you're interested in, high speed and high data throughput cameras, do get in touch with Tucson because, yeah, they have a very impressive range when it comes to high speed cameras. Just to quickly introduce as well, a setup that we have in our Birmingham office, put together by my colleague Alex, for imaging flows. And this is a microfluidic flow cell with a dispersion of fluorescent particles so that we can flow through it and image it with various cameras and put into practice some of the things that we'll be talking about in this presentation. Just to quickly give some of the properties of this. We're using a 10 times objective and they're 1 micrometer particles. It's on our own open frame microscope from Ken Research, but we're very grateful to Zaber for loaning us the linear motor stage, which we're using as a syringe pump. And we'll be seeing some data from this setup throughout this presentation. So what is our goal as we're imaging these moving samples? What are we aspiring towards today? Ultimately, we're trying to capture images of things that move that are crisp, have high signal-to-noise ratio, are free from artifacts, and look good. And whether that's in a flow, as in on the right-hand side here, or more of a sort of tile and stitch application, or whatever it might be, that's our goal. Also, just to briefly introduce this sample that we see on the left-hand side here, very unlikely that you'll have seen this before. This is simply a test slides that we use a lot in the Birmingham office that is dots of highlighter pen on a microscope slide. It's very nicely fluorescent and quite dramatic looking. So yeah, we'll be using this a few times in this presentation. So what are some examples of the technologies that we have, the camera technologies that present different issues, that overcome some of these issues? And one of the most important ones for imaging things that move is the global shutter camera. I'll be introducing each of these things in a bit more detail later on, but the brief summary for global shutter cameras is that every pixel starts and stops its exposure across the sensor simultaneously. The same is not true for rolling shutter cameras, which are a very common camera technology where images are read out row by row, typically starting at the top and then rolling down to the bottom, and both our exposure start and end typically rolls down in this way. Historically, rolling shutter cameras do have higher quantum efficiency and lower read noise than global shutter cameras, meaning that these are very much go-to technology for high sensitivity applications, and also they are the simplest to manufacture and therefore are found in practically every smartphone camera, and most consumer photography cameras as well are rolling shutter cameras. We have a trick that we can play, though, with rolling shutter cameras to avoid some of the artifacts that we'll be talking about later on and have them imitate global shutter cameras. I won't go into detail here, but ultimately we have an illumination technique that we can do to achieve a global-like behavior on a rolling shutter camera. And we'll be exploring when we can and can't do this and what some of the implications of it are. Finally, we have an entirely different way of running a camera, an entirely different camera technology called time delay integration cameras and time delay integration imaging. In short, this is a higher sensitivity version of a line scanning technology. It's capable of capturing very fast and with really nice high sensitivity, especially compared to line scan. But I'm not going to go into detail about it right now. We'll explore what this is later on, because it does take a bit of getting your head around. And yeah, for a lot of people, we've not come across this before. So we're exploring what it is, how it works, and what it actually means for us. So on to now the first of our problems in a bit more detail, motion blur. So of course this happens when, during the camera exposure, signal is spread across multiple pixels because our imaging subject is moving. In a microscope setting, it might look a bit more like this. Once again, we have our highlighter pen sample here where we're moving down. During that movement, our light from our sample is being spread across multiple pixels. To understand how we can sort of quantify this and quantify what's going on, and also very usefully for other imaging artifacts we'll talk about later, we want to think about how we can quantify motion in our images in general. And what we're going to suggest for this presentation, at least, is that we think about motion in terms of pixels per second. So whatever it is that you're capturing in your imaging, the motion of that object, of your imaging subject, if we convert its motion into pixels per second, here we have a few examples of different pixel per second motion speeds, just to illustrate what we're talking about. We can either measure this movement from images, if you've got a movie, a sequence of frames that you can measure it from, or you can, of course, calculate how many pixels of the camera's image your object will move per second, based on knowing the pixel size and the optics involved, especially the magnification, and understanding the motion. If you know, oh, this moves X micrometers per second or meters per second or whatever it might be. And here, of course, we have a very simple formula for working it out. This then allows us to very simply define our motion blur, where we're going to suggest a useful metric for motion blur is just its length, how many pixels it's spread across, which, thanks to our speed of motion, it being in pixels per second, all we need to do to calculate that length is multiply that speed of motion by the exposure time that you're using, and you end up with the length of a motion blur. And if, for example, you had quite long exposure time of, say, 500 milliseconds, and you had a 10 pixel per second motion, you'd end up with a 5 pixel motion blur, which is probably going to be too long for a lot of people. That's really blurring a fair amount. So then, of course, to reduce that, all we do is reduce our exposure time, assuming that, of course, you can't change your speed of motion, which would also be an option. If we reduce our exposure time by a factor of 5, we now only have 1 pixel of motion blur length, which is far more likely to be acceptable. But, of course, we've now reduced our exposure time by a factor of 5. That has massive implications for the amount of signal that we've collected. So ultimately, motion blur in imaging is this compromise between how much motion blur you can afford on the one hand versus how much signal you need to capture on the other. And how much motion blur you can afford entirely depends on your application needs. If you, for example, need high detail resolution and accurate pixel level signal measurements where your signal measurements aren't spread across multiple pixels, distorting their true value, you want to aim for, and this is a rough rule of thumb that we're suggesting, but you want to aim for less than half a pixel of motion blur across your images. But as I've mentioned, the exact needs for high precision resolution and for the resolution of your system to match what you might, for example, calculate optically, your needs for that will vary for applications. And the relationship between your microscope optics resolution and then motion blur affecting resolution is a complicated one. We're not going to dive into it today, but what we can have a think about is what different levels of motion blur might look like, and so long as we stick to pixels per exposure in this case units, we can expect fairly similar looking results no matter your imaging subject, because it's simply how many pixels does the objects blur across. If we have a stationary object, we of course have 0 pixels of movement. Whereas as we start to increase the motion speed or increase the exposure time, we can end up with, here we have 5 pixels per exposure of motion. And we can see that blurring is significantly affecting the resolving power of our system here. And as we get into 10 and even 50 pixels per exposure of motion, things are getting a little bit silly. There's probably not many imaging applications that can work here at 50 pixels per exposure. So the question then is how to reduce motion blur. As we've already mentioned, we reduce the exposure time, but this isn't so simple. If we have too much blur and we reduce our exposure, we can end up having too little signal, having too low a signal to noise ratio. And the key question then becomes, how can we avoid going below the minimum viable signal to noise ratio that you can handle for your application? How can we get nice, high quality, high signal to noise ratio images with minimal motion blur? And ultimately, there's 5 different methods that we can do this that we're going to suggest. The first is the broadest and the one that I'm going to say least about today, but it is, of course, just to improve the light throughput to your camera, whether that's through optics, through having higher quality optics, or whether that's through, if you're able to, increasing the strength of the illumination. There's, of course, countless methods to bring more light to the camera and therefore be able to reduce your exposure time without affecting your signal-to-noise ratio. But let's leave those aside and think about, what we as a camera company can talk about. One of the methods by which we can improve our signal-to-noise ratio and allow you to reduce exposure time is increasing the quantum efficiency of the camera. This is simply the likelihood of detecting any photon that lands on the camera. And if we have a quick sort of comparison between a system that had 70% quantum efficiency and we increased that through a change of camera technology to 95%, you can see that we reduce the exposure time that we'd need to use by about a quarter. A factor that has rather ambiguous impacts and we'll have to think about on a more case-by-case basis is reducing read noise. For many sort of high-end scientific-grade cameras which have read noise of less than around 2 electrons, reducing read noise, at least at the signal levels which I believe most people are working at when they're imaging flows, reducing read noise is not going to have any meaningful effect really, like a very minor effect. However, if you're more on the sort of high-speed cameras end of the market, read noise here can be measured in the tens of electrons. And at that point, if you're able to reduce read noise, either with a different camera mode or moving towards a more scientific grade or a more low light specific camera, that can have a really significant effect on your signal to noise ratio. So that's well worth considering. The other method, though, is increasing pixel size. And this can, of course, be done optically or through binning. But if you did it through increasing the actual physical size of the camera pixel, we can think about if you had, for example, a 6.5 micrometer pixel, and then you increase that to an 11 micrometer pixel, both of these very common camera pixel sizes on the market for high-end scientific cameras. This increase would lead to a roughly 4 times decrease in the exposure time that you would need to maintain the same signal-to-noise ratio. Of course, that is at the cost of resolution, as your pixel size is now bigger. But that's again a trade-off that you have to consider for your own application. The final method, though, is talk to us, because there's numerous different caveats and thinking points about all of these different factors, and we'll be very much able to talk you through the specific requirements that you have for your example and for your application, and how these different factors can come into play. A last couple of considerations, though, for sensitivity, and thinking for the first time about the differences between our rolling shutter and global shutter cameras, which I briefly introduced earlier. Historically, global shutter cameras, which have many advantages, as we'll explore later on, these are front illuminated. I'm not going to really dive into what this means, but in summary, it means lower quantum efficiency. And as we can see from this example of a real front illuminated global shutter camera, it's wavelength dependent quantum efficiency. The peak is around 63%, something along those lines. And due to the way front illuminated sensors are made, we have almost no UV sensitivity, and relatively low quantum efficiency across the board compared to the back illuminated cameras, which are available if you're using a rolling shutter architecture. These are really not really found in global shutter devices for physical reasons to do with the design of sensors. And if you have a back illuminated sensor, your QE curve can look a bit more like this. And as you can see, this is a massive increase across the board, and especially in the UV, where we go from nothing to quite a lot. And also in the infrared, here we're looking at a difference in quantum efficiency of a factor of sort of 3 or 4 in between the front and the back illuminated sensors. So depending on your wavelength detection needs, you can have a really significant improvement by having back illuminated sensors. So global shutter cameras, of course, have their advantages for reducing, or in fact completely eliminating, the rolling shutter artifacts we're going to talk about soon. But bear in mind that that's not the only factor that's different between these two camera technologies. Rolling shutter cameras can really bring sensitivity advantages too. So there's plenty to think about. Again, talk to us if you're in any doubt about how to prioritize these different factors. So in thinking about the problems that we encounter, we've now ticked off motion blur, we've talked about low signal. Let's dive into these rolling shutter artifacts and explore how these happen and how we can reduce them. So what we have with rolling shutter artifacts, and here once again we have an example more like what you'd see on the microscope system. You have something moving fast relative to a camera shutter that is rolling from top to bottom. And what exactly that means, we'll explore in a second. But its typical manifestation in microscopy is if you have something moving from left to right relative to a shutter moving from top to bottom, you end up with a shear that you can see in this object that should normally be roughly circular, or you can have them either stretched or compressed vertically. So to understand how that happens, we need to understand, first of all, what a shutter is. Ultimately, the shutter is the thing that starts and stops the exposure, that says, right, discard any charge that's built up previously and start collecting charge for the frame now, and then at the end, stop exposing the camera to new signal as it lands on the camera. These can be both mechanical and electronic. They are separated into two types. The two types we've already been talking about, that's both rolling shutters, which start and stop their exposure row by row, and global shutters, which start and stop the exposure simultaneously, as we've mentioned. So for how our global shutter camera works, once again we start and stop the exposure across each row simultaneously. This gives us a really nice fast response if we're trying to synchronize with other events, and of course cuts out any rolling shutter artifacts, as we'll show in a second. And these are then mainly found in physics, industrial and high-speed applications. But as we explored before, this method does give us historically lower quantum efficiency and higher read noise compared to rolling shutter cameras. Now, rolling shutter cameras have a different pixel transistor design, and this leads to this behavior where we roll the exposure down from the top to bottom, both for the start and the stop. Sometimes you can also have sensors that are split in the middle and roll in both directions from the middle outwards. This is called a split sensor design. And as we've already mentioned, the rolling shutter design allows us to back illuminate these cameras, giving us higher QE, and they can also have lower read noise. These cameras are therefore dominant in markets where high sensitivity, high quantum efficiency is really valuable. And to understand the implications of this and understand our rolling shutter artifacts in a little more detail, we need to understand quite precisely the timing of how these rolling shutters operate. This diagram on the right-hand side, sort of parallelogram diagram, you'll see this a lot in sort of camera manuals and things discussing the operation and timing of rolling shutter cameras. And what it shows is the y-axis, as it were, is from top to bottom of the sensor in the rows of the sensor, and then the x-axis is time. And this roll is just the same as the animation that we've been seeing previously, where the start of an exposure rolls from top to bottom. We expose for a certain time for every row, and then once that first row has finished its allotted exposure time, the roll again starts as each row finishes its exposure time. How fast this whole thing operates is determined by the line time. And if we were to zoom in on this diagram a little more to see individual rows, we'd see the starting of each row after the last, and indeed the finish of each row, is separated in time by 1 unit of this line time. The total time to roll, the shutter roll time here in the diagram, is given by the line time times the number of rows. And it's in fact this time to roll and in extension this line time that determines the speed that our cameras operate. This is 1 divided by the frame rate, this time to roll. And that's exactly how we can find out our line time. If you don't know it from camera specification sheets or otherwise, we simply have 1 divided by the frame rate times the number of pixels in Y, and that can tell us our line time. So now onto our rolling shutter artifacts, and in fact for the vast majority of applications within scientific imaging of rolling shutter cameras, these artifacts are mostly negligible, but that's mostly outside of the case of imaging things that move. And here we do have to at least calculate whether or not there will be an issue, whether our images will end up looking like this. So how do we calculate whether they're going to be negligible or completely unacceptable like this? Once again, it slightly depends on the application and on the job that you're trying to do for how we calculate how significant these are. If we are trying to do this left-hand job here, where we're trying to capture objects moving relative to a stationary camera, or in general, maybe smaller scale motion that's happening in some places across our image, here we have different considerations compared to these other 3 jobs. In this case, where our motion is not uniform across our imaging sensor, some of the key questions are: how far do objects move during the roll of the shutter? So as that shutter's moving from top to bottom, how far do the objects actually move during that time? Also, how many rows of the sensor do the objects cover? We can imagine that smaller objects are going to incur less artifacts than larger objects. So the key point is comparing the size and speed of objects to the speed of our rolling shutter. Here we've got a nice T for tungsten sample, which is going to move slowly from left to right, and a much faster rolling shutter, which is going to attempt to sample it. In this case, our shutter speed is much greater than our object speed. And as we can see, providing our shutter speed is much faster, we get an undistorted result. You can imagine that if this T for tungsten was 10 times taller, and the red line was moving just the same speed, we might start to end up with artifacts even at this speed, because the height is also important. But in this case, our shutter is more than able to keep pace. However, if the object's speed starts to approach or even exceed the shutter speed, we can end up with just the kind of artifacts that we've shown. If that's a horizontal motion, the artifacts might look like this. And hopefully you can see from the interaction of the red line and the T how this image is formed. If, on the other hand, they are vertical distortions, we can end up with this stretching of the object. If the motion was in the opposite direction to the rolling shutter, then the stretch would be in the other direction, would be compressed. Quick note to remember that the speed of our object motion we can characterize in pixels per second, as we introduced earlier in the presentation, but our speed of our shutter in pixels per second is just 1 divided by the line time. So it's really simple to work out once you have that line time. So the key question is, how fast is your sample? Moving on now to the other 3 jobs that we've thought about for our characterizations of imaging things that move. In all 3 of these cases, it might be much more common and much more expected for our imaging subject that's in motion to fill our entire field of view vertically. And in this case, we do have to think about things slightly different. But fundamentally, the considerations are the same. But this consideration of whether we want to synchronize imaging across the whole frame, we don't want one frame time delay between the top and bottom of a sensor. It does add considerably to the requirements to reduce rolling shutter artifacts. The motion of the whole frame from top to bottom during that read time must be very small. If, for example, we have a PCB, a circuit board that we're trying to image that's moving from left to right, with a global shutter camera, we'll just get a nice, proper snapshot of this object, whereas for a rolling shutter camera we might end up with this shear effect as we've rolled from top to bottom, and the amount of this shear will depend on the motion speed, of course, in pixels per second, multiplied by the height of the frame or the object that we're trying to image in pixels, multiplied by the camera line time. So what do we do if rolling shutter artifacts are too large? To improve them or remove them, we have 4 methods. First of all, for rolling shutter cameras, through a changing camera technology, or in some cases changing the mode that your camera is operating in, you can significantly increase the speed of the shutter with a faster camera. Through changing camera technology, across scientific imaging, there's orders of magnitude a difference in the line time of cameras, depending on whether they're intended for high-speed scientific applications or not. So big decreases in artifacts can be possible. However, if you need to eliminate them completely while still using a rolling shutter camera, if you're able to, you can use a pseudo global shutter. What exactly we need for this and how it works and what it means, we'll explore on the next slide. But we can, of course, use a global shutter camera. And this just completely eliminates rolling shutter artifacts. There are none. It's no longer a thing. The last thing we can do, though, is potentially change to TDI technology. And once again, this is something we're going to discuss later. But to dive into the pseudo global shutter a little bit more, what this is it's a timed illumination technique that avoids rolling shutter artifacts with rolling shutter cameras. And it's achieved through hardware triggering. And what we need, of course, then is a triggerable low latency light source that can switch on and off very quickly, at least much, much faster than the rolling shutter of our camera operates. How it works is actually illustrated fairly well by this little animation that you've seen before, where as the camera is rolling, the light source is actually turned off. And only once all of the pixels are exposing does our light source turn on. What that means is, so long as you don't have any form of background light from other sources, no photons reach the camera while the rolling effect is happening. And we only have photons reach the camera when every row is exposing and we're behaving like we're a global shutter camera. To dive into this a little bit more, we have once again one of these parallelogram diagrams where we've got the roll of the sensor from the top to bottom over time on the x-axis. Here we can see that we have to wait in darkness with the light source turned off for that roll to happen, and then once all the rows are exposing, we turn on the light source. We have some amount of real exposure time, you could say, like genuine exposure to light, which we'll call the pseudo global time on this diagram. I'll also, for shorthand, call this the exposure time for the next few slides, because this is, when we're actually exposing the camera to light. It's this period given in green here on this diagram. And then we once again roll out the end of the exposure and simultaneously the start of the next one in darkness once again. So when can we use this technique of pseudo-global shutter? When is this likely to help us? Well, this is actually a rather complex question. And one of the factors in that question is that pseudo-global shutter adds delay between our frames, which can affect the frame rate that our camera can run at. This delay is in fact given by either the exposure time that we want, the light on time, or the camera's frame time, whichever is shorter. And I'll show some diagrams in a second to illustrate how that can be the case. But what this means is that either very short or very long exposures will experience less delay with a pseudo-global shutter mode compared to their ordinary operation, and that the delay is largest when the exposure and the frame time are set to be equal. In the case of frame time greater than our exposure time, here we have once again a parallelogram diagram, rolling shutter in normal operation on the top, pseudo-global mode on the bottom. You can see that in this case our frame time given by the angled portion of the diagram is maybe roughly 5 times the exposure time given by the length of this line. With our pseudo-global mode operation, this exposure is of course happening at the same time across all of our pixels. If, however, we add in multiple frames with our rolling shutter camera in the rolling shutter mode, we're able to start the next frame as soon as the bottom row has started its exposure, or one line time later we're able to start the next frame exposing. For our pseudo-global shutter mode, however, we've got to wait for the frame time, then the exposure time, then the frame time, then the exposure time. And this can add up to some small delay between the end of our final 3 frames here. And as our exposure time gets shorter and shorter compared to our frame time, our impact on the frame rate gets less and less. If, on the other hand, we have a frame time, which is much shorter than our long exposure time, similarly, we have some delay, but less delay. And as our exposure time gets longer and longer, the impact of that delay on our imaging gets lesser and lesser. However, if, as in this case, we have a exposure time which is roughly equal to our frame time, here we have the maximum impact, where now we're having to wait for the exposure time, the frame time, then the exposure, then the frame, then the exposure. In this case, our frame rate is roughly halved compared to what the camera can achieve in rolling shutter mode. So when your exposure time is roughly equal to your frame time, your delays are much bigger. Now, whether this is actually a big delay for your application, of course, entirely depends on your camera, on your application needs, on the frame rate that you're trying to run at, all sorts of factors. But this most significant detriment, as you could say, for pseudo-global shutter mode in most cases is the need to add this additional delay. Otherwise, so long as you've got your high-speed triggerable light source, whether that's an LED or a laser or whatever it might be, then pseudo-global shutter mode can completely eliminate rolling shutter artifacts with rolling shutter cameras. So it's a mode with a great deal of potential, providing your scientific camera supports it, which I'd say the majority of them do now. So that's our main technologies covered with our sort of conventional area scan cameras for how we can meet some of these different problems and overcome them. Whether it's our global shutter cameras, our rolling shutter cameras with its higher sensitivity, or this pseudo-global shutter mode that we can use with most rolling shutter cameras. We do, however, have this final technique that we can do, and this is time delay integration. So, for time delay integration, we do require one of these 3 jobs on the right. We cannot, with TDI cameras, for reasons which will hopefully become clear as we explore how they work in a few slides' time, we can't do these jobs where motion is in unpredictable directions with unpredictable velocities. But in these other three modes, jobs where we're likely to understand what's going on in terms of movement within our sample quite well, this is a very potent ground for TDI to be used. So what actually is TDI? Well, it is, as I've mentioned before, ultimately a line scanning technique where we have a almost one-dimensional camera that, in order to produce a two-dimensional image, we move our imaging subject, in this case a T-photoxin, past the camera. If we were to zoom in on what's going on here, for a conventional line scan camera, we'd have just one very long row of pixels, and our imaging subject would move past that row. What TDI cameras do differently, however, is it's not just one row, it's multiple rows, what we call stages. And once again, our T-photoxin moves past each stage. Now, what's special about that? Let's zoom into what actually happens with a TDI sensor. So here we have a movie of how a TDI sensor works. In this case, we've just got a 5x5 pixel TDI sensor. In fact, a real camera such as the 9K TDI by Tuxin is 9,000 columns by 256 rows, or what we call in TDI stages. But for this simpler case, let's see what happens. Ultimately, what TDI does is, as light from our imaging subject comes in, and the imaging subject moves across the sensor, the signal that we've captured is moved along the sensor at the same time. We have acquired photoelectrons in each pixel, which we physically move across the sensor in sync with our moving imaging subject. What this in effect gives us is the ability to expose again, without motion blur, as our imaging subject moves. We can have the number of times more exposure as we have number of stages. In this case 5, we've had 5 times the exposure time we would otherwise have. Real TDI cameras have many more stages than 5, so can really increase sensitivity by exposing more light at each row. In the case of modern sCMOS TDI cameras, we have CMOS style readout electronics at the end, which with high speed and low noise, at least compared to line scan and previous TDI, we can read out our detected signals. So we build up that 2D image one row at a time. So comparing line scan and TDI cameras very briefly, we can use TDI cameras for the majority of the same applications as we could line scan cameras, but because of this significantly better sensitivity, we can use them in low light applications too, just like the jobs that we've been exploring today. And this is why you might well not have heard of TDI cameras before, because sCMOS TDI is a relatively new innovation, and this brings back illumination and low read noise to TDI, alongside the really high speeds of CMOS readouts. So we can now bring this really impressive and valuable technique into more low light focused scientific imaging. And that's largely down to this ability to have multiple stages. If we had a line scan camera, we just have one chance to expose our light as it moves past, or indeed an area scan camera as well, where we're setting our short exposure time to avoid motion blur. With TDI cameras, our exposure time, if we've got 256 stages, can be 256 times longer than an area scan camera, trying to avoid motion blur as our sample moves past. So to see an example, here we have a very common and again very powerful application for TDI cameras, and that's scanning large samples. And the key thing here is that unlike area scan cameras, which have to of course stop at each point as we form our tile and stitch, we don't have to stop the stage. We can avoid stage settle waiting times, and with, in this case, a say 4 millisecond exposure, capturing 3.7 gigabytes of data, a 2 gigapixel image in 10 seconds, thanks to that non-stop motion for each of 10 strips going back and forth across this sample, again, of highlighter pen. And you can see the level of detail that we're acquiring here in this 2 gigapixel image in 10 seconds. And this is with fluorescence. And yeah, the power of this technique is really impressive. There are, of course, many other applications where we can use TDI technology. TDI is great ultimately for imaging things that move. and whether that's moving samples and flow, such as flow cytometry, where it is in fact the technology of choice in a lot of imaging flow cytometry applications, or stitching, as we just saw, or constant monitoring applications where we might be doing this ongoing analysis, live analysis of something that's undergoing motion. Ultimately, all we need for doing TDI is either predictable or measurable uniform movement. We need to either be able to say, okay, we know the imaging subject is going to be moving at, say, 20,000 pixels per second past our camera. Let's set our camera to run at 20,000 pixels per second so that they're in sync. Or, for example, you can have many microscope stages have an encoder output, which can tell a camera exactly how fast the stage is moving, and then no matter what speed that stage is moving at, the camera will be in sync with it. We can, of course, therefore use TDI with flows, where in a microfluidic device, our speed is predictable. And this is just a quick example of our TDI camera in our office, set up on our flow cell, capturing fluorescent beads as they flow past. And in this case, we've captured a 65,000 pixel tall image just in one shot. Just set up the camera and run it for as long as you want. And capture your image of your particles or cells or whatever it might be moving past. Great potential with TDI for capturing flows. So on to our key take-homes and our summary for our webinar today. Very important point is not to confuse motion blur and rolling shutter artifacts. As we've explored today, these very much make most sense to be explored separately as separate issues, where our motion blur is given by the motion speed multiplied by the exposure time. Reducing our exposure time, of course, reduces our amount of signal that we'll collect, but there are various methods we can take to increase the signal-to-noise ratio that we're able to capture. Rolling shutter distortions entirely depend on the speed of that sample movement and its size, and the camera shutter speed as it scans down it. But global shutters and pseudo-global modes, if you can use them, completely avoid these rolling shutter artifacts, but at the cost of some sensitivity in the case of global shutter cameras. Also, we have this technology of sCMOS TDI, which can be very beneficial for capturing things with this uniform or predictable motion. Finally, if you're left in any doubt about how all of these concepts apply to your imaging application, or if you want more detail about anything that we've talked about today, do get in touch with us for application-specific advice. A final note to introduce some new products that Tucson Photonics are demonstrating at Photonics West, which is happening in San Francisco in January next year. On the side of TDI sCMOS, they already have the 9K TDI and the 9K TDI Pro, which are brilliant sCMOS TDI cameras. But adding to that range, we have the Gemini 8 and the Gemini 16, which are 1 megahertz line rate cameras, meaning 1 million rows per second. So very, very, very fast readout. And these are both back-illuminated scientific-grade TDI cameras. For rolling shutter cameras with, again, these large format, high-speed, high data throughput cameras, there's the Leo 3243, which is 3.2 micrometer pixels, and 43 million of them, which is, again, back illuminated and runs with that large format sensor at 100 frames per second. Then we have the Aries 6510, which is an excellent high-quality sensor, back illuminated, high quantum efficiency, 10 megapixel, 6.5 micron pixel camera. Again, a large format sensor. And finally, we have a global shutter camera coming out, the Libra 3414, which is 3.4 micron pixels and a 14 megapixel global shutter sCMOS camera. But a last quick note for if you are coming to Photonics West, there's a new and super exciting sCMOS for high-speed applications coming out. I can't tell you anything more about it here. If you're interested, do get in touch with Tucson. If you're able to come to Photonics West, do come along and check this out. But with that, thank you very much for your time and your attention during the webinar today. I'd be very much welcome any questions that you might have. But thank you very much for your time and enjoy the rest of your day.